Hello, everyone. My name is Yuwen, a graduate student from Xiang University of Science and Technology. It's my pleasure to introduce our work here. First, I will introduce the motivation of our work. 3D object recognition has made significant progress in various applications, including robotics, shape analysis, and autonomous driving. There exists a lot of work for point cloud recognition, especially point-based methods have been extensively researched. However, this static setup impedes the model application in the real world, where classes of 3D objects arrive in continuous streams. As shown in the figure, a home assistance robot pre-trained with abundant instances can only grasp the predefined objects in a clean environment. It needs to continually recognize new categories of objects which may have occlusions, cluttered backgrounds, and poor quality point cloud. However, new classes often consist of few-shot samples and there is a domain shift with the base classes. Our paper is focused on the challenging cross-domain few-shot class-incremental learning setting. The incremental sessions contain few-shot samples from the real world, while the base session contains many synthetic 3D objects for training. The proposed setting mimics the few-shot and domain shifts that commonly exist in the continuous learning process for real-world applications. We first give the proposed framework. The model in the base session is trained with a cosine classifier on a large synthetic dataset. In the incremental sessions, part of the parameters of the model is tuned with few-shot real-world samples. At inference, samples are first identified as the base or new classes and then passed to different branches of the model for prediction. Most methods use a linear classifier in the base model and optimize the standard cross-entropy loss. However, as shown in figure, when training the base model with standard cross-entropy loss, the maximum logit exhibits less distinguishable information between base classes and new classes. There is a large overlapping area between maximum logits, and it is hard to classify the base and new classes through the logits. Additionally, since the logit outputted by the linear classifier is unbounded, it is hard to define a logit threshold, which is crucial for classifying base samples and new samples. When we replace the standard classifier with a cosine classifier, the maximum logits are bounded and are more discriminative between the base and new classes. Some methods freeze the whole backbone and only train the new classifier layer to avoid forgetting base classes. However, when base classes and incremental classes come from different domains, only fine-tuning the linear classifier layer cannot guarantee the good performance of the new classes. As shown in figure, when only training the classifier layer, the accuracy of new classes is much lower. As shallow layers tend to learn generalized representations, we only fine-tune deep layers. To further alleviate the forgetting of past new samples, we use a small buffer that stores only one instance per past class. As soft labels contain more information than one hot labels, we also store the logits of the old model for past samples. Although soft labels contain more information than hard labels, we also use hard labels as auxiliary information to avoid the misclassification of the soft labels produced by the model. It is an effective way to avoid the incremental model mimicking incorrect information from the previous model. Through the hard label and soft label replay, the model can preserve more information about past classes. A robust base model should have a high response for base class testing samples and a low response for new class testing samples out of the distribution. It is supposed that the output of the base model has a lower response to new classes and a much higher response to base classes. Thus, we use the output of the base model to detect base classes and new classes. We set the label of all base class examples as 0 and all incremental samples as 1. By convention, samples with higher scores are classified as base classes and vice versa. As we get the predicted task ID, we can decouple the base classes and new classes testing. We use 4 3D object classification datasets, including 2 synthetic datasets ModelNet, ShapeNet, and 2 real-scan datasets CO3D and ScanObjectNN. As shown in table, our approach outperforms other proposed methods by a large margin. LWF, which retains no old examples, performs worst due to its severe forgetting of past samples. Since FSCIL and IL2M store limited old samples, the performance drop of base classes is much lower than LWF. Our method outperforms FSCIL and IL2M both in the learning of new classes and the ability to maintain the classification ability of base classes. While the performance drop of base classes is the lowest, in fact, the performance of new classes is the worst. Our method strikes a better balance between learning new classes and maintaining base class performance. Furthermore, our approach outperforms recent work on FSCIL for 3D object recognition, with a higher average harmonic accuracy of 55% versus 20%. When we replace DGCNN with point clip as the backbone, the performance of the new class increases due to its excellent performance for few-shot point cloud recognition. We compare different training methods on the base session and evaluate their ability to detect base classes and incremental classes. We regard base classes as ID data and all the incremental classes as OOD data. As base classes and new classes detection is a binary classification problem, we use one standard metric, area under the ROC curve, which is widely used in evaluating binary classification performance and also commonly used in OOD detection tasks. We report the class-wise average accuracy and harmonic accuracy. For the OOD score, we adopt two simple but effective score functions, MSP and MLS. As shown in upper left table, using the cosine classifier achieves the best OOD detection performance of all the compared methods, and the incremental performance is the best. We also compare our method with other detection-based methods, including confidence-based and learning-based. The confidence-based method compares the maximum probability of the base model output and the incremental model. As shown in lower left table, the harmonic accuracy of the confidence-based method in each session is nearly 10 points lower than our method. The harmonic accuracy of the learning-based method is extremely lower than our method due to the binary classifier tends to classify all the examples to the base classes. We compare three fine-tuning ways: 1. Only fine-tuning the classifier layer, 2. Fine-tuning the projection layers with the classifier layer, and 3. Fine-tuning the whole network. Besides that, we also compare our simple fine-tuning methods with one cross-domain few-shot learning method. As shown in upper right table, the harmonic accuracy is the highest when fine-tuning the last three layers. Fine-tuning the last three layers outperforms the second best results, fine-tuning the whole network by up to 4.9% in the last session, as it can somewhat avoid overfitting. When fine-tuning the last layer, the channel importance method outperforms the fine-tuning ones, but the whole performance is much lower than fine-tuning the last three layers. We are curious whether our approach still performs well when the new class samples and base class samples come from the same dataset. As shown in lower right table, the high average accuracy has confirmed that our method can generalize to the standard FSCIL learning. This paper focuses on how to balance the performance of base classes and new classes during the FSCIL process for point cloud recognition, where the base session may contain many synthetic objects, and the coming data is from the real world. We discriminate between the base and new classes from an OOD detection perspective and use the maximum cosine logit of the base model as the score. Then, we adopt the two-branch structure to avoid catastrophic forgetting of the base classes. By discriminating base and new samples to achieve parameter isolation, the model can better adapt to new classes without sacrificing the performance of base classes. To better mitigate the forgetting of incremental classes, we adopt the soft label and hard label replay together to retain the performance of past new samples. We conduct extensive evaluations of the proposed method on 3 synthetic to real point cloud datasets, and the results show the superiority of our proposed method. Thanks for listening.